Hi, everyone. Thanks for coming out. Skip the first couple of slides because it's kind of already done for me. But yeah, my name's Jake. I'm a software engineer at Red Hat. I work in the virtualization team. I mostly work on a project called libkrun and the associated projects along with it. But I think the first thing we should do today is talk about what exactly is confidential computing. First off, data encryption technologies aren't a new thing in our industry. We have storage encryption that protects your data at rest. We have network encryption that protects your data in transit. But what about your data in use? And when I talk about data in use, I'm talking about the data that's in your CPU registers, the CPU cache, and actually in your RAM. Well, confidential computing is the protection of data in use by performing computation in a hardware-based, attested, trusted execution environment. And trusted execution environments, or TEEs for short, there's different ways you can implement them. But the industry has converged towards implementing TEEs through virtual machines. And this is just proved through the fact that it's easier and honestly just more convenient to pour your applications towards them. So really what our goal here is, it's to provide data confidentiality and prove through something called cryptographic proof or attestation that what's running in your VM is exactly what you're expecting. And like I said before, there's different ways you can implement a TEE. And of course, each chip manufacturer has a different architecture for how they create their VMs. And because of that, I'm going to focus on two different chips, Intel TX and AMD SEV-SNP. ARM and IBM and RISC-V all have different architectures, but for the talk today, that's going to be out of scope. So first off, I want to kind of outline what does a standard VM look like. For the sake of the talk, we'll call this an untrusted VM. And on the host, you have your host kernel, you have your physical hardware, think your CPU, your devices, your storage, and then there's also a hypervisor. And then on the guest, you have virtual firmware, you have a different guest kernel, possibly. You have your emulated devices, and then you have something called shared memory, which is memory that's accessible between the host and the guest. The issue with these untrusted VMs is you're susceptible to attacks from basically every direction. You have to worry about other cloud tenants. You have to worry about people with physical access to the system, possibly a malicious sysadmin, rogue devices, and let's be real, even accidents. But the goal of confidential computing is to mitigate these risks through hardware assurances. So in a confidential system, we actually start off with the same kind of basis. We actually don't trust the guest right off the bat. But what we do trust is something called the hardware root of trust. This is basically just a certified piece of hardware that has the ability to actually measure the contents of the VM and then sign it with a key that's provided at manufacturing time. And then we also depend on something called an attestation server. And this also has to be trusted from the start. And basically what we're doing is this attestation server is going to validate the measurements and prove two things, really. One, that the hypervisor didn't lie and that we're actually confidential. And two, that we're running only what we're expecting in the VM. So there's no extra memory. There's no random binary that showed up. So we can really break this whole process down into a couple steps. First off, the guest is going to communicate with the hypervisor on the host and ask for an attestation report. The hardware root of trust will provide the attestation report. This is going to include, like I said, measurements and a key. And then the guest will provide that report to something called the attestation server. The attestation server will then compare it to some reference values it has. And as long as the measurements match up and we can actually prove that we're running confidentially, then the attestation server will provide the guest with keys that it can use to then decrypt the root volume and then possibly other devices as well. So that's kind of the quick rundown of what the confidential computing architecture looks like. So I think now it's a good idea to talk about some of the projects that Red Hat has been contributing to in this space. And I do just want to make a quick disclaimer that I'm not going to be giving a deep dive into all these different technologies. Each one of these could be their own presentation here today. But if you do want a little more information than what I'm going to give today, my manager gave a talk last year. He goes into more depth there. And of course, you can ask questions or find me in the hallway after too. Okay, so the Linux kernel is really the cornerstone for all of the work that I'm going to be talking about. And without the Linux kernel changes, none of this is really possible. So guest support came into the kernel first in version 5.19. That includes SNP and TDX. SNP was first to the punch on host support in the kernel, which was in 6.11. And then most recently in 6.16, TDX host support was merged. If you're looking for a more enterprise solution, all of these changes are also in CentOS Stream 9 and 10. I just want to really reiterate the fact that this was a lot of work going into this. This was years and years and hundreds of patches to get in. So just massive kudos to those people involved. But now that those changes are in the kernel, other tools can start taking advantage of the functionality. So things like QEMU, which is a really popular open source VMM, supports SNP in 9.1 and TDX in 10.1. And then libvirt follows suit with SNP support in 10.5 and TDX support in 11.6. But what if the workload you want to run in the guest doesn't support these cutting edge Linux kernel versions? Well, in that case, you're going to want to use a Paravisor. And the project that we see filling into this space is called Coconut SVSM, or Secure VM Service Module. And SVSM is really a guest firmware component that provides you with secure services and device emulations to the guest operating system in a confidential VM. At the moment, there's no official release for SVSM, but the team has been doing monthly development releases that are actually leading up to this official release. One of the really big efforts that's going on right now in this space is to come up with a complete attestation solution with a stateful vTPM. And then we're also working towards adding host kernel support for SVSM. This is going to be planned for early 26, hopefully. I do also want to point out one important thing about SVSM, and it's that currently it only supports SEV-SNP guests. There is some ongoing work and discussion surrounding TDX support, but that's still very open-ended at this time. Another thing that we need to consider is before the VM even boots, we need to be concerned about security through the boot chain. And we can do this by extending SecureBoot to actually cover the init ramfs and the kernel command line by using something called UKIs, or Unified Kernel Images. And basically, this is helping us prevent things like someone swapping a binary on us that could be malicious. And this is helping us prove that no objects in our boot chain were altered. And this can prevent attacks on the guests before the OS is even booted. There are some inherent limitations with UKIs in that things like the kernel command line or the init ramfs are immutable. So one thing that we're working on right now is essentially to find a way to whitelist the kernel command line or the init ramfs to provide some more flexibility in that sense. So I've talked about attestation a little bit up to this point, but when we talk about attestation, there's really two projects that we're focusing on. The first one is called Keylime, and Keylime is a CNCF hosted project, and it provides you with highly scalable remote boot attestation. Then it also provides you with runtime integrity measurements, and this opens the door up to something called runtime attestation. And then another project that we're contributing to is called Trusty, and Trusty is a confidential containers project, and it can provide you with components to deploy on a trusted system to do remote attestation as well. So in this area, another big effort going on is in combination with something like SVSM, we want to use both of these tools to do attestation. First off, we want to do pre-boot attestation with Trusty to actually unlock the root disk. And then after the initial boot and the initial attestation to unlock the root disk, we want to use Keylime to do subsequent runtime attestations to continuously validate the integrity and the confidentiality of the system. So I've been talking a lot up to this point about VMs, but we can actually extend the VMs to enable cloud-native confidential computing workloads at the pod level. And we can actually do this with something called confidential containers. And confidential containers is a CNCF sandbox project, and it can help you seamlessly deliver confidential workloads via multiple trusted execution environment platforms and development models. I think AI is really popular right now, so maybe it would help to contextualize this a little bit. So let's say you have a workload in two pods. You have maybe an inferencing pod and a training pod. One thing you have to worry about in a standard VM scenario or standard scenario is maybe a malicious sysadmin wants to snoop on maybe your model parameters or your model data. Well, what we can do is we can encapsulate those pods in these confidential VMs and prevent external entities from getting unauthorized access to anything. So what we can do with confidential containers is actually sign the container images to prevent them getting tampered at launch. But we also require the workloads to have secrets to perform their operations. So before we can actually do any training, we need to decrypt the training data. Or before we do any inference, we need to decrypt the trained model. And these are separate keys also. So the only way we can get these keys is by a successful attestation. And confidential containers is a really big project within the Red Hat space right now. We're at the point where we're starting to hopefully distribute it out to customers soon. Confidential clusters is very similar to confidential containers, except that confidential clusters focuses on integrating confidential computing tech into Kubernetes clusters. And this uses something called image-based Linux OSes and bootable container images. And the premise here is that before a new node can be added to a cluster, it also has to be successfully attested. So OpenShift confidential nodes on CVMs is offered with SEV-SNP and TDX on Google Cloud Platform in OpenShift version 4.19. The CVM offering with SNP on Azure in OpenShift 4.19 is also available. And then TDX will be in version 4.20. And similar to a lot of the other projects I've talked about today, the investigation into remote attestation is constantly under development. This is a really hot space where there's a lot of discussion and POCs going on. So with all of these different projects that we have, there's of course an attempt to limit the amount of code rewriting and reuse of really just writing the same code in multiple places. So with that, we created an organization on GitHub called Verdi. And this is where we house all of our shared libraries and tools. For example, we have Rust libraries for SEV-SNP, TDX, and also some other architectures I said I wasn't going to talk about, but ARM-CCA and AWS Nitro. And what this does is it allows us to create a really easy interface for people to actually bring up these VMs programmatically, rather than having to go through all the different KVM APIs. We also have CLI tools to interact with SNP hosts and guests. And of course, these tools are continuously under development. The TDX library was our latest accomplishment. Like I said before, we have our CCA and Nitro libraries that are in development right now. And then we're also planning on adding other CLIs for different architectures as well. Primarily, TDX is of concern right now. So one of the main consumers of these libraries and tools I just talked about is a project called libkrun, which is what I mostly work on. And libkrun is a dynamic library that provides you with virtualization-based process isolation. And libkrun is a Rust-based VMM, which is the host portion of a hypervisor. But it actually provides the user with the C API. And libkrun VMs are really just micro VMs. So what this means is we're really shooting for low footprint, low memory footprint. We have a minimal kernel. We have minimal devices that are emulated. And we've implemented SNP, TDX, Nitro, and CCA into libkrun. So it's a really well-rounded confidential computing solution. But what makes it interesting is it's so heavily integrated into the container ecosystem. We've extended the crun runtime with something called the krun runtime. And this interfaces directly with the libkrun API. So if you're on a TDX host, for example, you can use Podman like you normally would, and the container that you'd bring up would be encapsulated within a TDX VM, which makes it really, really easy. So wanted to leave it nice and open for questions since I covered a lot of topics.
So
No, you're fine. You won't hear yourself.
It's for the recording.
Oh, okay. All right. Those who are online can hear me then. In a confidential VM, is both the code and the data encrypted at rest? So when it's in memory,
In use.
in use.
Confidential focuses on data in use. Something like Lux would. Okay. The question was, in a CVM, is the data and code at rest encrypted? Confidential VMs focus on data in use. The technology that would be worried about data at rest would be something like Lux encryption on a disk.
Okay. But you do need to decrypt it before you do operations inside a CPU, right?
Yes.
Okay, so it happens at the CPU.
Yes, you do need to decrypt the root disk before you can actually do anything in the guest. So, really basic example is in a confidential VM, let's say focused towards a container workload, you would have an attestation agent built into the init RD. So right when the init process starts, it will do the attestation, and then once it unlocks the root disk, then it continues to boot as normal.
Okay. So let's say if you have a web server running in a VM, that application data is encrypted in RAM.
Yeah. So
And
if
then
you have a web server running inside the guest,
Yeah.
your question is what's running on the web server encrypted?
Yeah.
Whatever is in memory at the time would be encrypted, yes.
Okay, and then it gets decrypted before it's in the CPU. Because I don't know if you can do operations on encrypted data. Like if you have numbers, you need the numbers.
Well, think of
For
it
that.
like the question was surrounding how the encryption works within the guest vCPU. Correct?
Yeah.
Think of it like the memory is encrypted from people outside of the VM. The VM itself can see what's going on inside the guest.
Okay.
So think of it like if I run a confidential container with Podman, in theory, a normal Podman container's memory can get snooped on by some other process. By wrapping it around a confidential VM, that memory that you can technically dump in a non-confidential state would just be mumbo jumbo. It would be unreadable.
Okay.
Does that make answer?
Yeah, that makes more sense. Okay. All right. Thank you.
I like on all the different topics.
Or just what you said so for anything.
I don't have one slide with everything. No, sorry.
I do have a
Sorry. The previous question was, do I have a slide that lists all of the different topics I talked about? And no, I do not.
You said it uses.
You're fine.
Okay. Yeah, you said it uses bootable Linux container images. Is that boot C?
My understanding is it uses the same technology under the hood
Same as what?
as Bootsy, but I'm not
Okay.
100% sure. I don't work on that area of the projects, but if you want to talk to me outside, I can figure out for you.
Thanks.
What are the areas where you're looking for more assistance, and what are some of the problems that require more external assistance from the Red Hat team?
It's a great question. It was around, where can other people step in and help, and where do we see the most help needed from the Red Hat point of view? I think that from the SVSM point of view, I'll go back to that slide. Right now, it only supports SNP, and I think from our point of view, we see this as a really good option as a generic solution. But that also means we need people like Intel TDX to have support there, RMCC to have support there. Whether that happens is kind of depends on other people as well. I think the topic of attestation is always an area that has ongoing development going on. Everything is still very much up in the air. And we've been working on this for years. So I would say definitely those two areas are, from my understanding, that kind of need the most TLC still. Any other questions?
How are you guys going about like making it easier to do the UKI stuff that you were talking about with like being able to actually modify the command line and then in MMFS? Is there like a project that's like doing that has like a better way to modify UKIs and still not break the signatures and everything?
Yeah, so the question's around, how are we making it easier for people to make UKIs less difficult to work with? I know we do have people working on it on the confidential clusters side of things, because that does make heavy use of UKIs. But in terms of specifics, unfortunately, I don't know. But I can find out for you.
Okay. Yeah, because I know that bootc, bootable containers themselves are looking into that, like making sealed images, and so if that gets better, that's good for them as well. So that's it.
Any research being done around ARM?
The question was, is there any research being done around ARM? CCA to be specific. We do have people working on not only reviewing the CCA patches upstream. I think those are getting really close to being done. There is ongoing CCA work in libkron specifically. We have a library that works so far with the patches that are upstream. And we do have a POC that works with libkron as well, so we are able to create confidential VMs with CCA. But where things are still kind of fluid upstream, nothing's really solidified yet.
Still have time for questions.
Try to leave plenty of time for questions. A lot of topics. If there's any other questions, you can find me around. Thanks, everyone.